So my point is metadislocations and approximants. So to express and to explain what I have to do today, I need to go through two steps. The first step is to go to some very old stuff on approximants, symmetry, strata, and cell decomposition for you to understand the next step, which is dislocations there. The first step, so it will go fast, but I still need it. It's my basic tool for understanding the dislocation. Before understanding a dislocation in something, I have to describe the thing first, okay? So that will be done now. And of course, some conclusion. We all know that. Many quasicrystals have a phase transformation, or several phase transformation at low or high temperature from quasicrystal to crystals, and these crystals can be seen as periodic versions of the parent quasicrystals. There are most of them, or many of them, are in group-subgroup relationship with nice lattice parameters that are coming from the Z model of the parent quasicrystals. And these who are in group-subgroup, I will call them approximants here. So I'm not really talking about clusters, but just approximant as being what we see here. This is a standard cut and projection along an irrational direction in a lattice in 2 dimensions here. So if I make now the cut along a rational direction of the lattice, then I will have a periodic object, which will be called an approximant. From going to here, from here to here, I just have to make an oblique cut. I will call that the cut space. This is R space. And to make the approximant, I go fast on that, okay? We had these atomic surfaces. We had our physical space here. It was in the parent quasicrystal. We make the approximant by making the cut along a rational direction. So we have the new atomic surfaces. One point I would just to emphasize is that we have to reshape atomic shape in order to keep the same connection. You see the black and the black here are connected by phazon, easy phazon, and the red will be connected also by easy phazon. And the generation process will be, we still use the same projection on E parallel. That means that we will have the same clusters, the same Z model, the same atomic positions. But now we will look at the projection along a space that is perpendicular to the cut. So it's an oblique space with respect to the old one. Okay, that's just what we have to do. What happens there? If you look in this perpendicular space, which is perpendicular to the cut, I will call it perpendicular space of the approximant, okay? This is what you see in the quasicrystals. There is a lot of points coming in. It makes a dense set of points. If you look along rational direction, then all points align, and they form now lattices. In this, if you move the atomic surfaces, you will generate a uniformly dense set of points, and you will generate especially homogeneous distribution of phasons. Each time a point goes out, each time a point anywhere goes out, another one comes in. Here, if you move these atomic surfaces, nothing will happen, except if you hit one point. So in one case, you will have a uniformly dense set of phasons. In the other one, you have a regular lattice, and the phazon field is no longer distributed. So that's what Mark said. There is no phazon fluctuation in this periodic. I would say there is no phazon fluctuation homogeneous, but you can have bound coming on, just because one point comes into it. So that's what is my main point here for discussing metadislocation. Now let's just go through some understanding. You have a lattice, that is the lattice of the approximant. It's a set of vectors, the Z model, that are such that their projection on the cut space just leave them invariant. Now the symmetry operation. Symmetry operation of our symmetry operation of the lattice, if they leave invariant the cut space, EC, and I made a possible symmetry of the lattice. So you'll see they are not necessarily fulfilled. You will see that. So what we have to search is take all the G symmetry operation of the quasi-lattice, of the quasi-periodic object, the parent quasicrystal, and make the commutators. And see which commutators are zero. This will be the G vector, the symmetry operation that will survive. Now there is a last thing I need is a structure pattern. So what I said is that when you cut along a rational direction, If you look perpendicularly, it also is a lattice. You see a lattice that way, so I see a lattice this way. And so you see this is a lattice. Each point here is a projection of the whole L lattice in our real space. So you see that. That's exactly the same drawing as the first one. So I will call the structure pattern all the points X here belongs to L perp. This is this lattice. And that are inside the atomic surface. I call it sigma prime because it's deformed, okay, slightly deformed. And sigma prime depends on where you put it. So I take an arbitrary unit as being the origin. I will just displace sigma prime by z. So it's sigma prime z means sigma prime displaced in perp space anywhere. Okay? And these, all of these points, this point, and so on, they generate a L translation orbit. So a full orbit of points in the real structure. And if you look at these points, you list these points, it's exactly like listing the Wyckoff position with respect to translation only. Okay, so I take the example of the octagonal tiling. It's n equals 4, it's group P8M. Everyone knows about it. Just you may not know, I don't know, that it's indeed a very old tiling. It's been found, a stone has been found in the Suleiman in Iran. That sketch on octagonal, if you look, it's fantastic. It's really an octagonal tiling. There are even pheasants. The guy who did that said, oh, no, I should switch. And up, he made a pheasant. 5th century. Today, octagonal tiling is very used. Look, this is a full octagonal tiling. Square meters of octagonal tiling. Sorry, in Abu Dhabi. So they are doing that. And if you look there, it's a correct one, is a good one. Of course, there are pieces that are all the same. Just if you take octagonal tiling, so it's octagonal, you have a mirror like that, M1, M2, mirror M prime, M prime 2. Here are the matrices. If I take M1, the first vector remains. Second vector transform into -4. It's here. The third into -3, and my 4 into -2. This is a matrix, etc. So what I will do is apply exactly what we said. Take a general projection. Say that this projection should have a trace equal to 2 because we are working in a plane, 2 dimension. That if, since it is a projection, the square must be equal to the matrix itself. And for if I want to make the 8mm stratum, I just write the commutation between M1 and M prime 1. If I want M prime, okay, I make the commutation, or M prime make this commutation. If you do that, you have a set of equations which are easily solved. The first one leads you to the standard 8M projection with cos pi over 4. And the second one here I'll give you for the 4mm prime because I will use it. This is the projection PC. Okay, now we have it explicitly. And if you want to make it periodic, what you have to do is write that cos phi is P over N, B is Q over N, P, Q, and N are integers. Of course, it must be such that P squared plus Q squared equal N2. And simple solution is 4, 3, 5. 4 squared plus 3 squared is 5 squared. Here it is. You see the lattice L prime projected in perp space. Everything I show you is perp space. That's in real space. And here is one of those structures. When I say one, is for the following reason. Now, let's go. I take one atomic surface centered at that point. I am in perp space, always, okay? I looked Marjorie. I copy it at this point, and we'll copy all along the line. Good. Now, this line, I'll copy it everywhere. On the second line, you see, here it's copied, etc., etc. I finish with this kind of drawings, and these are the K drawings. This kind of drawings, of course, is periodic, and you look just at one, you have a set of lines, and each time you cross line, you generate a phason, of course, because you are going out of an atomic surface and come into a new one. And if you carefully do that, if you look at that, now we will make the things. So you have small cells. Let me just say it again here. You have a cell here, a cell there, and so on. You have, it's a partition of the plane, okay? So this was the structure pattern. Each time I go from one partition to the other one, I lose 1 point of the pattern PZ. Maybe I gain another point, but it's different structure. The cell will be the set of the Z position. You can move sigma prime without removing a point or integrating a new point. You have space. Okay, it's not like in quasi-crystal, you move it, you generate phasons. Here not. If you stay into a cell, you generate no phasons. So this is the cell. If I take one cell and take all the symmetry elements that commute with P and that such that they globally keep this cell invariant, I get the space group of the approximant. So that means that there is not one space group, but several. Here, for example, for this previous case, we had the structure of P4GM, PG, P1, PM, M prime, and so on. So it's not one structure. There are several structures of the same stratum. That's a point. For example, if I take a point here, I generate the structures. This is the atomic surface of a window. These are the points of the lattice in pulp space. Here I reproduce the small pieces that you have seen before. Okay? What kind of mirror I am expecting? I have a mirror that passes here, and it does not hit any of those points, or any point is transformed into another one. So it means that it's a G mirror, because no points can be left invariant. On the contrary, if I take this cell, you see the mirror passes through points. This structure is PM. It has a mirror there, and probably other things. But it's just to show you that these two approximants of the same stratum are different. So I'm going to metadislocation. Okay, this is what Mick said. I think everyone recognized what he said. B is a parallel part plus a paired part. And the question is, and one is elastic, and the second is a phason. I will look, of course, to that one. This is a perfect dislocation in the octagonal tiling. You see the dislocation is here. You can make a Burger vectors, a Burger circuit directly on it, just by counting here along. You will see it's open. Metadislocation. To me, metadislocation of Burger's vector B in an approximant, a given approximant, is a dislocation of the parent quasi-crystal. So I take the dislocation B, it's here, with the Burger vector B. This is, in blue, the standard way of looking at the dislocation in the quasi-crystal. Now I will do the same. I take B, make the same projection, very same projection in parallel space. It will give the same Burger vector with same length, with everything same in parallel space. But now I look at this Burger vector in this space, not anymore in that one, in this space. In that space, that's space where all phasons have collapsed on a lattice, and I will connect a point of a lattice to another point of a lattice. And I say that I have a meta-dislocation if this component, P perp, along this red, is non-zero. If the component is 0, then we just have a perfect dislocation of the approximant. It's normal dislocation. Because in non-zero, and because it is not a lattice vector of the approximant, a meta-dislocation must be the border of a set of phason boundaries. And I will show you they mostly would appear in dipoles connected by phason walls. Here is a perfect object. It is a 4mm, not M prime, M prime. Very simple approximant, 4mm. Here is a dislocation. What you see is that this 4mm has this unit cell, and I draw an arrow here. You see it's a elementary phason that points that way. Square, rhombus. It's here. Around the dislocation, you have this structure with the square rhombus that way. Now here, you have the same structure with the rhombus that way. In that part, it has a rhombus that way, and in this part, again, that way. So there are three structures here. Of course, this structure fits totally, perfectly together. The same Z model. I would call that meroidal, perfectly meroidal twins. But they are not. There are three different structures. Oh, I'm sorry. Here there are three variants of the same structure. This is the drawing in perp space for this 4mm, which I didn't show you. It's very easy. So here is, Here are the points of the lattice perp in perp space, and here are all the limits of the approximants of the atomic structures. Sorry, I'm starting from there. I have a B perp that is non-zero, so it's a vector here. It goes to here. This is a 1, 0, 0, 0 perpendicular, the 1, 0, 0 Burger vector. You see, from here to here, nothing happens. Now here I will make the real structure. I start from 0 and I will draw a circle. The circle with B phi going from 0 to 2 pi. Okay? It's B 2 pi and so on. B theta over 2 pi. So I will turn around. From here to here, nothing happened. That's here. We are in that structure. This structure with this arrow. That's the arrow here. Here we have a boundary. And now we go from phi1 to phi2, we go into this structure with a arrow vertical. And phi2, here we have a new boundary. And we go in a structure that has this region. And finally we go back, because this and this, of course, are periodic. Finally we go back to the first structure. But in between, what we have done is one step in real space. So what happens here is we have 3 boundaries. We made 3 boundaries, and these boundaries are directly seen in the perp space. How did it work? Look, we start from that. First step, phi1 goes that. Second step, phi2 goes that. Third step goes that. It's finished. Between this and that, we made just one step. Here was the structure. You see just forget about the colors. The black ones, the black octagons. Okay, you see that? And you see here, there is a lozenge. So what I will do is take that here, take this one here. 3 small, very small jumps, okay? Does not cost much. And I get the blue one, which is thus displaced by 1 unit. Here, for example, is an amusing calculation of a dipole of these 2. Here is one dislocation, the other one is here. I'm sorry for this. There is 1 point missing. I don't know why, my program. What you see here are the 3 boundaries which we just discussed. So we are expecting points having metadislocations and boundaries in between. These boundaries are the image of the boundaries of the atomic surfaces in the approximant. And I have a picture, beautiful picture by these 2 guys, by Mick and Mark. And I think, Mark, you will show some much better ones or very recent ones. But that looks very much like what I am expecting. A dipole with all these lines. And to me, what is wonderful, that this line you see, Marjorie, there are the traces in real space of things that are in perp space, of atomic surfaces. So if you are clever enough, but just by looking to their so beautiful picture, we should be able to say, oh, I know where the atomic surfaces are. I'm not smart enough. So, and just for fun, I wanted to show you a more complicated, here it's again the 4M prime and prime 4-3, okay? It's much larger than the one we saw. There are not 3 jump that case. And we will take the Burger vector 1, 0, 0, 0, the simplest one. This is a Burger vector that will take this whole structure, which is quite complicated, and move it just one step. The question is, forget about everything I said, how can you, just by phase and jumps, make it moving with a minimum number of jumps, and to have everything coming back? And the answer is, go to perp. And if you are in perp, you start from here. You recognize here the drawings I've shown you several times. This is 1, 0, 0, 0, 0 translation of the B perp. And so what I have to look at is draw a line. It does not necessarily has to be a straight line. It does not necessarily has to be a connected straight line. Actually, you connect a cell to another cell. Okay? But when I am in that cell, for example, I can move anywhere there. I won't change anything. So the connection you have to do is connect cells together. And do it in a way that you connect the less possible number of cells. It is achieved when you take a line. And now, of course, if I start from there, I will have this particular 1, 2, 3, 4, 5, blah, blah, blah. But if I move it a little bit, I will have different jumps. So there are several ones. Here I can count how many different gems there will be with just 12. And 12 is the minimum number. And I show you the 12 just to prove that it works. So we start from this. We have to make jumps, for example, you see of this kind of object. There are objects where we can do, wait a minute, where is those? Here, of course, etc. So if you look, I don't see it, but I have made a grade region of these 4 objects. So what you see from what we are starting, because after a couple of ways we will be lost, okay? The first step is this. So you remember my drawing? We go from 1 to 111 through 12. So you see it was there before, and now it's here. It's the same structure, of course, and it has moved by 1 unit. It's okay. So that means that if you have this kind of tilings, if you have to make a game or a puzzle, if you do it in paired space, you have the solutions. This was for to exemplify fun, because that's fun, of course. By the way, if we would have that to look at the electron microscope, we would have expected at least 12 of those lines, which is very, very much. So as a conclusion, I would say that I would propose to, of course, metadislocation is proposed by Mick and Knut and Mark. I didn't invent the term, it's your term. But I would say that we call metadislocations quasi-crystalline dislocations that are in approximant with non-zero per value in the approximants. I don't know if we are talking about the same thing. I am pretty sure, but I am not totally sure. But, well. They have Schrödinger vector. They all belong to the same Z model. So you'll see, you'll get the very same bigger. And they bound phase and walls and go to classical twin boundaries or classical partial dislocations. But it's more or less twin boundaries because the structures are different between these two, usually. So we may expect thinning. That's very easy to be written because once I read your papers, I saw you found it already. Most probably they should be as dipoles, even if one of the dipoles is very far away. And they should play a fundamental role in plasticity of those complex intermetallics. By the way, what I am expecting is that if we understand that, as you did, this could be generalized to other structure where there is no parent quasicrystal, but there is still an underlying Z model. So it's just a way to try to open these things to other things than approximants. So thank you very much for your attention, and thank you, Dan.